It's Physics 40S time with Dr. Carroll, Unit 6, our review lecture. So we're going to review some of the kinds of questions you'll find on our unit test about electrostatics. In our booklet, we are on page 25. So here's some of the equations that will be helpful to you during the test. So the first is Coulomb's law. The electrostatic force is equal to KQA/QB over RAB squared. Remember, it's a vector, and so that's one that's helpful. And we also know that that is equal to QB times the electric field due to QA. We also have the proportional Coulomb's law equation, where the new force is QA new over QA original times QB new over QB original times R original squared over R new squared times F original. Now, you aren't necessarily changing all three of those parameters each time, but this is another useful equation. So you'd be given the original force and then various parameter changes and get the new force. So then we looked at electric fields, and the electric field is KQA over R squared, and the units are newtons per coulomb, or volts per meter, as we saw later on in the chapter. So also the electric field is force over Q. I'm talking about QB, fine. So then F is QB times the electric field. We also looked at sharing of charge, electrification by friction, definition of basic law of electrostatics, guts of the atom, and next we went to electric potential energy, which is KQA/QB divided by R. And let's go down more here, the units in joules. Then the work is always the change in energy. We saw that even in the last unit. Work is KQA/QB, 1 over R final, minus 1 over R initial, which is then just the change in electric potential energy. And the electric potential is KQA over R due to A, and of course we could look at compound potentials if we wanted, which is also the electric potential energy over QB. And the units of potential are joules per coulomb, which are also known as volts. We looked at voltage, which is the change in potential, so it's the final potential minus the initial, and it also equals work over Q2 or QB. So in general, work equals Q times the voltage. I know W's get confused because sometimes they're work, sometimes they stand for watts. In the uniform electric field, and I should put a circle around this, in uniform electric fields only, well, except for F equals QE, but voltage is the electric field times the distance between the plates. That's only for uniform electric fields. The work is Q times the electric field times the distance between the plates. Okay, those are for uniform electric fields only. The F equals Q times the electric field, that's for any kind of electric field, but if you substitute in electric field being voltage over distance between the plates, then F is QV over D, that is for uniform electric fields only. And we looked at the square root symbol there, that the speed of an electron or proton or any subatomic particle between two plates is the square root of 2 times the charge on the particle times the distance between the plates, times the voltage over the mass of the object. So one more time, the speed is the square root of 2 times the charge in coulombs of the subatomic particle times the voltage over which it crosses in units of volts over the mass of the object. Okay, so here's some questions. We're on to page 26. Let me just flip over there too. And so we'll look at 10 questions or so, similar to the kinds that you'll see. So we have one here where we're doing electrification by conduction. sharing charge. So this is one of those touching and separating. Very touching question here, isn't it? So I got QA is 8 microcoulombs, QB is 6 microcoulombs, and QC is minus 10 microcoulombs. So those are the initial charges. When we rearrange everything, it's 8 and 6 is 14 and minus 10. It still has to be 4 microcoulombs at the end, right? So, and it does turn out to be. So first we touch A and B together, so the average is 7, so each is 7. Now that A is 7, it touches C, which is minus 10, so that's minus 3 divided by 2 is minus 1.5. Then we take QC, which is minus 1.5, and we touch it to B, so we get minus 1.5 and 6, so that's 4.5, and divided by 2. So again, let's see there. 2.75, really? 2.75 times 2 is 5.5. Okay, so what did we have here? We had QC prime is negative 1.5, and QB was 7. So that's, 5.5 divided by 2 is 2.75. That's right. So it all works. Okay, so you'll come across with a question like that. So now you know how to do it. Okay, second example here. What do we got going on here? Calculate the net electric force, not electric field, but electric force on this charge here, C, in a right angle triangle. Okay, so it is 4 coulombs. A is 2 coulombs, B is 3 coulombs, and you see the legs of the right angle triangles distance. AC is 5 meters, BC is 7 meters. So the net force on C, so A pushes C south, B pushes C to the west. So it's going to be somewhere southwest. You plug in your Coulomb law calculations, and I'm not going to go through all the details here. Here I'm going to make the right angle triangle and use Pythagorean theorem. So my net force on C is 3.63 by 10 to the 9 newtons west, 52.62 degrees south. Now, if they asked you the electric field at that point, well, all you would do is take your 3.63 by 10 to the 9 newtons and divide by the 4 coulombs, because the 4 coulombs is right there, and that will give you the electric field at that point, and it would be in the same direction, but because they're both positive. Okay? But I'm going to definitely ask you the electric force. Definitely, yeah, sounds good. Okay. Example 3, here we have a collinear case where we have two charges. A is 5.6 microcoulombs, B is minus 6.3 microcoulombs. They are, R is so many centimeters between the two of them, and that is 40. That's 40 centimeters, or 0.4 meters. Oh, that 4 became a 9, didn't it? Try again. 0.4 meters. There you go. And then from B to a point in question is 10 centimeters. So, a whole bunch of things we can ask. The first is the net electric force on QB. So it's going to be to the left because A is attracted to B and B is attracted to A. But we want the force on QB. So A stays fixed and it brings B closer to it. So it's KQA QB over R squared. So 9 by 10 to 9 times 5.6 by 10 to minus 6 times 6.3 by 10 to minus 6 divided by 0.4 squared. And you get 1.98 newtons directed to the west or left. Okay, the second part wants to calculate the electric field at the star point. So that's the electric field of A at the star plus B at the star. So a positive test charge moves to the right due to A and moves to the left due to B. I'm using east and west, fine. So I get the calculation, and the west is going to win, right? Because not only is the charge larger, but the asterisk point is closer to B than to A. So I take the larger minus the smaller, and my value becomes whatever 5.76 by 10 to the 6 minus 2.16 by 10 to the 5 is. Shall we fill it in? Why not? So I'm going to live on stage here. 5.67 by 10 to the 6 minus 2.016 by 10 to the 5 is 5.4684. That's too many sig figs. Ms. NATO wouldn't like all these sig figs. I'm breaking all the rules here. 5.4684 by 10 to the 6. What are my units here? Newtons per coulomb to the west. Now in the next part, let's plunk a real live charge at that star point. So a minus 6 microcoulomb charge is now placed at that point. Calculate the force. So the magnitude is just 6 by 10 to the minus 6 times this, fine, they rounded it, 5.47 by 10 to the 6. So 32.82 newtons. A little tricky thing here, though, is that the electric field was to the west. I'm putting a real live charge here. If it was positive, then the force would be to the west, but it's not. It's negative. Okay? So if a real live charge is negative, your force is opposite the direction of the electric field, because recall the definition of electric field, the direction that a positive test charge would move. Okay? So, a little tricky thing there, but that's how it works. Example 4, I don't know if I'm doing these in the exact same order as we taught it, but it's all going to be there one way or the other. A 9 microcoulomb charge is moved 6 centimeters across a uniform electric field. The electric field magnitude, also called electric field intensity, 6 by 10 to the 4 newtons per coulomb. Calculate the work done on the system. So the work done is Q times V. Voltage is ED, so it's QED. So 9 by 10 to the minus 6 times 6 by 10 to the 4th times the distance that we're moving. So 3.24 by 10 to the minus 2 joules. And if you wanted to do more charge across those same distance and same electric field value, you do more work. If you had a steeper gradient, think of the electric field as like a hill a bit, and I know we talk about voltage like that too. The greater the electric field, the more work would have to be done. The more you're moving from one place to another, the more work would be done. So QED. Remember, this is only for a uniform electric field. In general, work equals QV. That's for any case. But the QED is just for a uniform electric field. Okay, on page 27 here, I'm going to flip to that page. And here we have a voltage, and it looks like we're not given the voltage, are we here? We're given, oh yeah, there it is right at the top. Voltage is 100 volts, and what am I pushing down here? Some positive charge. It appears to be a proton, yes. So the work done to push that down is QED. So how are we going to get all these things going on here? We know the charge of the proton is 1.6 by 10 to the minus 19. The distance between the plates is the voltage over the electric field, 100. The electric field, 1.875 by 10 to the 20th. Where am I getting the electric field from? Oh, it tells me the force. It gives me the force is 30 newtons. It's a uniform electric field. But in general, F equals QE. So the electric field is 30 newtons over 1.6 by 10 to the minus 19 coulombs. So I get 1.875 by 10 to the 20 newtons per coulomb. Okay, so I'm given, the stuff I'm circling here is what I'm given. So now I can go and take the work as Q, 1.6 by 10 to the minus 19 coulombs times the electric field, which I calculated, 1.875 by 10 to the 20th newtons per coulomb, times the distance between the plates. Now, how am I going to get that? Well, I got the electric field, so it's 5.33 by 10 to the minus 19, negative 19. Put a negative sign there. Okay, and that is just some practice on those style of questions, and I can even get the speed with which that proton hits the negative plate, right? It's accelerating towards the negative plate. 2 times 1.6 by 10 to the minus 19 times 100 over 1.67 by 10 to the minus 27, 1.38 by 10 to the 5. Let's put the units in, meters per second. Okay, So that is an example using uniform electric fields to calculate some important parameters about those. Example 6 is about electric potential. We want to calculate an electric potential at 6 centimeters to the left of a source charge 3.6 by 10 to the minus 17 coulombs. Okay, this is just a number. It's a scalar. It's not a vector. So phi is kqa over r, where a is our source. So 9 by 10 to the 9 times 3.6 by 10 to the minus 17 over 0.06. So 5.4 by 10 to the minus 6 volts, or 5.4 microvolts, if you want to be fancy about it. So that is the potential at the point 6 centimeters to the left of that source charge. Here we go, example 7. Calculate the voltage. Voltage is the change in potential. If you're now taking the evaluation of the potential to 10 centimeters to the left of that charge. Oh, so we're referring back to question. Oh no, we are not referring back to question 6, or are we? Let's see, 10 to the left of QA. Oh, I thought it said 9. Okay, source is QA. So yes, we are referring back to question 6. So at 10 centimeters, the potential is K, 9 by 10 to the 9. By the way, some books are going to write it as 8.99. Don't bother getting upset about that. It just rounds to 9 by 10 to the 9 times the source charge, 3.6 by 10 to the minus 17 over 0.1. Okay, so that's at 10 centimeters away. You get 3.24 by 10 to the minus 6 volts. Your initial potential was 5.4 by 10 to the minus 6. So the change is 2.16 by 10 to the minus 6 volts. Now that's going to be negative, isn't it? If I do 3.24 by 10 to the minus 6, 3.24 by 10 to the minus 6 minus 5.4 by 10 to the minus 6, I get negative 2.16 by 10 to the minus 6 volts. So put a negative sign there. And that is the change of potential, which is the voltage. Now a new fresh question here, example 8. Calculate the electric potential energy, E electric, of 2 3 coulomb charge separated by 7 meters. So if I could force 2 3 coulomb charges to be 7 meters from each other, they would have an electric potential energy of 1.16 by 10 to the 6 joules. K QA QB over R. 9 by 10 to the 9 times 3 times 3 over 7. Okay, that's lots of stored energy, isn't it? Okay. Example 9. Here we have a 3 microcoulomb charge 25 centimeters away from a 4.5 coulomb sphere. And then we want to see how much work was required to move it to that point if initially it was at 80 centimeters away. So how much work? KQA QB 1 over our final minus 1 over our initial. So 9 by 10 to the 9 times 3 by 10 to the minus 6 times 4.5 times 1 divided by our final is 0.25. Our initial is 0.8. So you put that in, and the work needed to move it there, you had to do that work because they're both positive, 3.34 by 10 to the 5 joules. The charges are both positive. Okay, now let's use the proportional Coulomb's law question here, example 10. And so we have QA is just some value Q, QB is some value 5Q. I'm not actually going to calculate the value of Q because I'm just looking at proportions. Your original, FO original, is 8 by 10 to the minus 6 newtons. So what's the new force if QA is doubled? Well, the force is directly proportional to the charge on A. So if you double the force, you don't even need to use that fancy schmancy equation. It's just 2 times 8, so 16 by 10 to the minus 6 newtons. Or in standard scientific notation, 1.6 by 10 to the minus 5 newtons. I can reset and calculate the new force if QA becomes AQ, so that's 4 times, and QB is half, so it would go from 5Q to 2.5Q. So 4 times and a half, so multiply those, you get 2. So it's 2 times, if QB is halved, oh, but yeah, it's half time because of QB, but QA goes up 8 times, so 8 times a half is 4. So 4 times 8, 32 by 10 to the minus 6, or 3.2 by 10 to the minus 5. So you have to look at every word there, right? Let's reset and calculate the new force if R is tripled. Okay, and I didn't do anything else. I just tripled the distance between them, so the force is going to go down, not by 3 times, but by 9 times. So the new force is a ninth of the original force. So 8 by 10 to the minus 6 divided by 9, or 8.89 by 10 to the minus 7 newtons. So expect a question like that. Then I'm not gonna flip the pages around for these ones here. You can, if you have a laptop, just flip it, or just tilt your head 90 degrees. You're going to have to draw field lines for maybe a uniform electric field, or a dipole, or 2 charges of the same sign. So make sure to put your arrowheads in, and in the ones with the dipoles or the 2 charges, make sure to put a few lines in all 3 regions, right? Don't just put stuff between them. Put stuff to the left of the charge on the left and to the right of the charge on the right. And remember to put arrowheads in as well. So not fancy drawings, but a few. And if you really want to get into this, you can look at the Phy40 website, and you can create various wild and wonderful electric field lines with 4, 8, 16, lots and lots of charges. Example 12, 500 joules of work is done to move a charged particle through 9 volts. Calculate Q. So the charge is just the work over the voltage. Okay, so we want to deliver 500 joules of work, and the voltage is 9 volts. So the charge that will accept that work would be 500 over 9, which is 55.56 coulombs. So bundle this in page 29 we did before, and 30. Those were out of place, but we did those before. So bundle in the review that we looked at with practice questions, assignments, etc. And you should do electrifyingly fantastic. Okay, it's not going to be a revolting result, but rather I think you'll get a charge out of this evaluation. Okay, have fun.